Hey there guys, welcome to this video. My name is Pushpinder Gill, and in this video we are going to be talking about the endogeneity problem in simultaneous equation models, right? So we're going to talk about the endogeneity problem in context of simultaneous equation models, right? So if you've seen the first video in simultaneous equation models, you must have seen that we came up with the two types of models for simple equations. So we had the quantity demanded. We had the quantity demanded at time t to be a function of price, which is beta price t plus the error term for the demand equation. And then we had the quantity supplied to be equal to, again, a function of price of again a function of price. So this is the supply equation, this is the demand equation, and using this in our previous video we found out the reduced form equation. So we actually found out the reduced form equations. I'll just write them down here, right? So the reduced form equations were that the price was equal to 1 over gamma minus beta into the error term demand, and minus 1 over gamma minus beta into the error term supply. And we also had quantity demanded to be equal to, this is actually under equilibrium conditions, where quantity demanded is actually equal to quantity supplied, which is equal to quantity. So this is me just summarizing the previous video. So if you haven't watched that video, guys, just make sure that you watch that video before you're coming to this video, so that we can carry it forward. So these were the reduced form equations that we got, right? So now you can clearly see that the price is endogenous in quantity demanded and in quantity supplied, because the price is a function of the error term of the demand equation and the error term of the supply equation. So we can clearly see that, right? So if we were to go ahead and estimate the demand equation, that is quantity demanded plus beta price plus the error term of the demand, you can clearly see that we're going to run into an endogeneity problem, which is that the price here is going to be related to the quantity demanded here, right? So that is the intuition behind the endogeneity problem in these kind of equations, in these simultaneous equations, because we had this equation, and then when we found the equation for price, we got price to be depending upon the error terms. And so this is the intuition behind it. So now let me just go ahead and prove this formally. Let me say that if you try to estimate, let's suppose you don't know about the reduced forms, right? So let's suppose if you try to estimate this equation using OLS, which is the ordinary least square, so what are you going to get into? So let's say, for example, you try to estimate. So you try to estimate the equation of demand. So let's suppose you try to estimate the demand equation, which is actually a function of price, and the error term by OLS, right? So let's suppose you try to estimate this by OLS. And so when you try to estimate that using OLS, so what are you going to get? What is the value of beta that you're going to get? So beta hat is simply going to be equal to summation of price and quantity demanded divided by summation of price square, right? So that's like the standard OLS. If you've seen the OLS videos, you would know how to find the parameter for the parameter beta for using OLS. So this is the parameter beta. So I'm just gonna write a subscript OLS to it. So this is what we get. Now we have to find whether this is consistent or not. So this is what we want. So under consistency, the probability limit of beta OLS should actually be the true beta, right? So that is what we want to see. We want to see whether this estimation using OLS is consistent or not, right? So what we're going to do, first of all, let's do one thing. Let's try to break it down. Let's try to find the probability limit. So if we want to find the probability limit of beta OLS, so we would want to find the probability limit of the numerator, which is sigma pt and qt, and the denominator. And we're going to assume that there are a total of t observations. So the observations go from t is equal to 1 to t. So there are a total of t observations. So this is t is equal to 1 to t, and this is t is equal to 1 to capital T, right? So we're assuming that there are t observations. Now, bear with me here, right? So let's try to find what is the probability limit of the denominator, right? So let's see that, what happens there. So what about the probability limit of the denominator, which is sigma pt square, and t runs from 1 to t, right? So that is simply going to be equal to, so you clearly, if you go back to the previous video, you can easily substitute that in the price equation. So if we substitute that in the price equation, what do we get? So that is sigma. So I'm not going to write the subscripts just to save time, and I'm not going to write probability limit, or let me just write that. So probability limit of sigma of the price equation. And what was our price value? Our price value was 1 over gamma in minus beta into the error term of demand minus 1 over gamma minus beta into the error term of supply. So this square is what we want, because we are actually doing the square. So let's say now this, what does this turn out to be? This turn out to be probability limit sigma, and then we just have to square it, which is the error term demand square divided by gamma minus beta square, plus error term supply square divided by gamma minus beta square, minus 2 times error terms demand, error term supply divided by gamma minus beta whole square. So this is what we get when we square it up, right? So this is what it is. Okay, so now if we try to take the probability limit inside, what we're going to be getting is the expected value of each of these terms. So it's going to be simply, so if we say what is the probability limit of summation of error term demand whole square, right? So what is that? So probability limit, so I'm just gonna write it in the box here. Probability limit of expected value of error term demand whole square, it's actually equal to the expected value of, so it's actually equal to the expected value of the error term demand whole square. Right, so that's what it is. So this is the expected value of error term demand whole square. So this thing over here is going to be equal to the expected value of error term demand whole square, right, divided by sigma minus this, sorry, gamma minus beta whole square, plus error term, same thing here, error term supply whole square over gamma minus beta whole square, minus 2 times the expected value of error term demand and error term supply divided by gamma minus beta whole square. So if you actually check out the assumptions that we drew in the first video when we set up this model, we assumed this to be 0, right? Because the error term of the demand and the error term of the supply are supposed to be independent. So this term goes to 0. So we're just left with this term. And if you go back to that video again, you would know that this term, the expected value of error term demand whole square, is nothing but the variance of this term, because the expected value of error term of demand is supposed to be 0. So this is the variance, which is actually equal to sigma d square. That is what we assumed. And what is this? This is equal to sigma s square, similarly, divided by gamma minus beta whole square. So this is the probability limit of the denominator, right? So keep that in mind, right? So now let's go back to the numerator. So if we go back to the numerator now, what was our numerator? Our numerator was probability limit sigma price and quantity, right? So this was theirs, that is probability limit sigma price versus quantity, right? So if you remember the expression for price and expression for quantity that we got in the reduced form, so this is going to be equal to probability limit. So this is going to get a little messy here. So that is going to be equal to the error term demand. Right. So what I'm going to do is I'm going to take 1 over gamma minus beta to be outside, right? So that's what I'm going to take out. So if I take it out from here, so this is nothing but error term demand minus error term supply, right? So this is the price This is the price. Price is error term demand over gamma minus beta minus error term supply over gamma minus beta. And what about the quantity? The quantity is, again, it's gamma into error term demand over gamma minus beta minus beta error term supply over gamma minus beta. So that gamma minus beta also comes out, and we have a square here. Remember, you have a gamma minus beta here, you have a gamma minus beta here. When I take them out, it's a square here. So I'm not going to write them here. So I'm going to write them here because they're constants. I can take them out. Now, this should become easy now. So if I try to solve this, this is 1 over gamma minus beta whole square. That is, again, probability limit, a summation of this into this, which is gamma error term demand whole square, this into this minus beta error term demand into error term supply, which is going to go to 0, this into this minus gamma error term supply error term demand, which is also going to go to 0, this into this plus beta error term supply whole square. So this is what we have. So again, if I take the summations and the probability limit inside, what I'm going to get expected value. So 1 over gamma minus beta whole square. What is this? This is expected value of gamma. Gamma is always outside because it's a constant, of expected value of demand square. Don't want to miss any steps. So what is the expected value of this and this? Again, we assume that to be 0. So that's 0. So this goes to 0. What is the expected value of this into this? Again, that goes to 0 plus beta, expected value of error term of supply whole square. So that turns out to be 1 over gamma minus beta whole square. That is gamma into sigma demand square plus beta into sigma supply square. So this is what the numerator goes to, right? So this is what the numerator goes to. Now things should be very simple. Now let's just club everything up. Now if we club everything up, what is the probability limit of beta OLS? The probability limit of beta OLS is summation of PT QT over summation of PT square, which we found out each to be equal to summation of PT QT, which was this. It's gamma sigma D square plus beta sigma S square divided by gamma minus beta whole square. So that is what the numerator is, and the denominator is, so what I'm going to do is I'm going to write the denominator as an inverse, because that's something can be written as PT QT into sigma PT square inverse, right? So I can write it like this because it's in the denominator, right? So that is nothing but sigma D square plus sigma S square over gamma minus beta whole square. You can see that this and this will cancel out because this is an inverse and this is outside, and this goes down to gamma sigma D square plus beta sigma S square over sigma D square plus sigma S square. All right, so this is equal to the probability limit of beta OLS. Now my question is that equal to beta, right? Or is that equal to gamma? Is that equal to either beta, or is that equal to either gamma? No, it is not, because this is the weighted average of beta and gamma. You're kind of taking the weighted average here. So if you're taking the weighted average here, this can never be equal to beta and this can never be equal to gamma. This would be somewhere in between beta and gamma. So this value is always going to be somewhere in between beta and gamma, and so that means this will never be equal to beta and this will never be equal to gamma, which brings us to an important point, that is that the probability limit, that means the probability limit of beta OLS cannot be equal to beta, which means our estimator is not consistent, which means we have an endogeneity problem, right? So that means we have an endogeneity problem. Right? So the problem here is the problem here is not OLS. The problem is not OLS, right? That's not the problem. The problem is completely else. The problem is that the value of beta and the value of gamma are not identified, right? We can still use OLS to simultaneous equation models, but we have to be careful. So the problem is not so the problem that beta and gamma cannot be consistently estimated. It's not due to the choice of your estimator, which is OLS. It is the choice. It is the problem of identification. That is, the value of beta and gamma are not going to be identified, right? So that's there. So which leads us to the second problem, which is the problem of identification. And what I'm going to do is I'm actually going to solve that problem, show that problem to you in the next video. So I hope you really understood this, guys. I hope you understood. Thank you very much for watching this video. Do make sure that you visit our website, that is perfect-course.com. Give us your valuable feedback at this email address, and like us, share us, facebook.com/perfectscores, and other social media platforms. So thank you very much for watching this video, guys, and I will see you in the next one.